Hello guys, and welcome to this channel. My name is Roman Narvaez. I am a civil engineer with a specialization in structural engineering. I am sending this workshop from the city of Gothenburg here in Sweden. And today the question is to explore. The question is does your steel frame connection will failure? And we are going to go inside this question with a first design of this. So we look at a simple connection. For example, we can use this column steel connection here to look at that. And we are going to define the loads here. We have a column here and we have a beam. We need to put the forces around this. So for example, in the B component or member, we are going to put some loads. So we look at that in the theta direction. We put, for example, 80 kilonewtons, maybe to the other direction, minus 80, perhaps a little horizontal force, right. We need to look at if the forces are balanced, and there are not. So we put a balance for these forces here. It could be an something like that. No, over there is -5. There. Here is 80, is 0, and the y direction -5. So right now we have the balance forces 0, 0. Right, we have a little moment, but we look later on. So we can make a calculation for this simple connection, steel connection. And at the first iteration, we are going to look some results here. Okay. What we are looking here is that yes, we get back to design to show you little green things here. The plate here is a thickness of 10 millimeters. This is the distance between these plates and column, and we have a bolt diameter 16. We have wells of 3 millimeters, and the strength of the steel is 355. To understand this, we need to look at to be able to read this result at the beginning. We need to understand some things here. The things that we need to understand is how can we predict failure. We can predict failure in for ductile materials and brittle materials, as you see in the picture here. We have for ductile materials, and we are using a ductile material of 355 megapascal. That's the stress and strain. But there are another kind of failure, which is in brittle materials. To predict failure, it's very simple for an axial stress body. You have the principal stress of sigma 1 here, but for a triaxial stress, is very difficult. So there are a lot of theories to predict this. And you have here, for example, this very complex this. For brittle materials, there are the purple ones here, theories, and for the ductile materials, we have the green ones. We are going to focus on von Mises and briefly Trescan. What means with that is that we have in the body test the principal stresses here, and we have the strength of the material, which is the yield strength and ultimate strength. So the the principal stresses, which are minimum and maximum, expressed in the form of strength of the material. That is something that you see here in the Rankine theory. We have the maximum stress and the minimum stress. Yes, the triaxial stress you can decompose into other ones, which is the stress causing a change in volume, and the other one, which is the stress causing a distortion in shape. The stresses causing a change in volume is called hydrostatic stresses. But we are going to focus on the stresses causing a distortion of shape in ductile materials. So what we can see here, the stresses in the hydrostatic here is equal in all directions, and you can see that, which is the average. I would like to focus on this matrix here, the principal stresses decomposed in the hydrostatic plus in the shape. We have a deviatoric stress component, which calls for the shape distortion. We need to take to erase or to subtract, that's the correct word, the hydrostatic stress. In that way you calculate these stresses, but we are going to go to the von Mises, which is our interest here. And von Mises says that yield occurs when the maximum distortion energy is equal to the distortion energy at yielding in an actual tensile stress. And this means very simple that we have a plane stress yield surface here, and the ellipsis is the von Mises field maximum distortion energy here, and you see here the principal stresses, and you have here a square strength of material in a square form, which means that is an ellipsis. So we are looking to these stresses in this connection here, and you see here that if you look at we have stresses here on the bolts, and we have stresses on the welds as well. And the high stresses in von Mises is in the red ones. So we need to check, for example, welds. How much do you have here on welds? You have almost 98.3, and you have 3 millimeters. So maybe we need to change that weld, and we go inside the weld, and we are going to change this to maybe 5. Yes, we can change the thickness of the plate. Alright, we make another calculation here. We check the von Mises again. The wells. What are you looking at? That is that the stresses has there are less down 83.2, and you see on the right bottom corner of this screen you have a diagram here, and you can look at that, and we are very safe here because I'm going to exemplify why. In the EU code we have a median of these stresses. When we are taking calculations for this, for example, here is a portion of the Euro code and the principal stresses for a well. In this control, they are taking a median value of the stresses. So which I mean, the median value, it could be there. So that it would be the equivalent stress. So when we look at our connection here, is very good. The plates, we can look at the bolts. The bolts has as well concentrated stresses over there. You see there, and they are around the utilization is 65%. No, sorry, this is the 82% utilization rate of that, right? That is von Mises. You are controlling the wells through von Mises, the plate as well. And you look at the plates here, and the percent is very good. So you can, that is for a simple control. We are going to look at another example here. For example, this analysis here, and we are going to look at the system line 5, for example. The link here, the connection over there. We have concentrate normal force here around 200 kilonewtons. We have moment, which is 110 kilonewtons per meters. We have shear force of 80 kilonewtons. I think this is going to give us problem when you are looking for, as you see here, we have a problem there, and we need to look at we need to make some kind of more stiff the connection over there. You have a problem here about the interaction between normal force and bending. So we need to make a design for this issue. We are going to open a project here. Oh, right. So as you see here, this is the connection, and we have some stiffener here. So in that way, the flanges will be more stiffer. Then we can look at around. You see there. So we can look at von Mises stress diagram. And you see that on the wells how much we have. utilization. We have a good margin here, very good. I'm looking there, so I can go yes, the plate here, and that's the well. It's only on the corner. The same explanation that you have before is that we have a very good well over there. Looking at the bone is strange. Right, that is for example for this kind of connection. If we look at another example here, this is two plates. The two plates are welded to each other, and you see bone misses here. Bone misses we have a very good marginal here, and you see the stresses, bone miss stresses are higher on the bolts, on the holes for the bolts, and maybe on the upper corner of this weld. In other workshop I show you this finite element calculation, and you see here we're seeing here, looking at the bones as well. We have a connection of steel column to a steel beam, and of course we have here some stiffers. Right here, so the web is getting more of these stresses, but we have a low stresses here, 136 megapascal. So this is a good design for this cantilever, for example, and very good. We can look at other things, but we are focusing here on the von Mises theory of failure. Right, that's the way. So I hope that you like this. I hope that give you more and more understanding of structural engineering. It's a very complex field, of course, and it requires a lot of years to master this field. Okay guys, so I hope that you enjoy this presentation, and see you around. Bye bye.